All right. This is the last topic for this chapter. Okay, let me explain to you what we're going to do today. You've been using, I've been talking about atomic masses. I even defined it for you. If you remember, on Thursday, I went over what an atomic mass was and how they got it. I said, pretend you're all periodic table elements. And I chose, who do I have as my standard here? Zach. Zach was our standard. I chose Zach because he was in the middle. You know, I could use him to compare people to. He was 150 pounds, or at least we said he was. Anyway. Well, the periodic table, the elements on the periodic table, we chose carbon to be our standard, and we compared everybody else to him. Why? Because carbon has all of those elements are really small. I mean, it's going to be something times 10 to the negative 20th grams. And a gram is a really small amount. So you're talking about a small number that I don't want to have to write down all the time. So what do? We made up our new scale. And that new scale was the atomic mass scale. But there's something you should have noticed about that. Maybe you did. Maybe you didn't. I told you at that time that carbon was our standard. So carbon, I told you, was told to be exactly 12 atomic mass units. Remember? You don't have to write this down. Okay, we already talked about this. But there's a problem with that. Carbon's supposed to be 12 atomic units. If he's our standard, if we chose him as our standard, why, when I look at the periodic table, does it say 12.011? It should say exactly 12. I chose him as my standard, just like I chose Zach as my standard. His 150 pounds is now 12. And then we compared everybody else to that. But I chose carbon as my standard and made him exactly 12. And yet up there it says 12.011. Well, there's a reason for that. That number here, that number here is not the mass of just carbon, 12. It's the mass, it's an average mass of all of the isotopes of carbon. Guess what? There's a lot of different forms of carbon. Okay, they have different numbers of what? If it's an isotope, it has different numbers of what? Neutrons, right. So basically, how many protons are in carbon? 6. All right, there's 6 protons in carbon. And there are 5 protons in boron and 7 in nitrogen. I can't change that number. If I take away 1 proton from carbon, what have I made? I made boron. If I add a proton to carbon, I've made nitrogen. However, the same carbon 12 that I picked as my standard, he has 6 protons and 6 neutrons. Okay, that's only one of the isotopes of carbon. Actually, carbon exists as 3 isotopes. You could actually have carbon 13 and carbon 14. Now, in carbon 14, how many protons are there in carbon 14? Still 6. But how many neutrons are in carbon 14? Yeah, 8. So I have to add up, I have to average all of those guys together to get that number. And notice that number is very close to 12. That's because most of carbon exists as carbon 12. And I'll explain that in a little bit too. All right, so let's talk about this last calculation we have to do, what's called the average atomic mass. The numbers you're looking at are averages. The numbers on the periodic table are average atomic masses. They are not the mass of any one particular isotope, but rather take into account all of the isotopes of a given element. Now I'm going to get rid of a misconception here. Normally when I say the word average, I think you all would probably do an average the same way. If I wanted to get the average height of people in this class, what would I do? Add up everybody's height and then divide by however many people I have in the class, right? I cannot do that in this case because everybody's not equal here. Let me explain why. Watch this now. Pay attention. Just because you're not, a lot of times I notice this, especially in this class, is that when I go off on my little tangents, a lot of times you think, well, I don't need to pay attention to this because he just said don't write this down. And for some of you, when I say don't write this down, it's like, you're hearing me say don't pay attention anymore until I'm done talking. That's not what I'm saying. What I'm saying is important, all right? Watch. Say, for example, I gave you a quiz. And you had, on that quiz, don't write this down again, it was worth 10 points. And you got a 90% on that quiz, okay? I gave a homework assignment. And on a homework assignment, which was also worth 10 points, you got 100% on that. All right? And then I gave a test, a chapter test worth 100 points. And you got a 50% on the test. Bad, yeah. Now, can I just add up those three and divide by 3 to get your average for the marking period? No, because the test was worth 100 points, the homework assignment and the quiz were only worth 10. What's your average going to be closer to? 50, 100, or 90? It'll be very close to 50. It's be very close to 50, be slightly above. These numbers will have brought it up a little bit, but if you average those out by just dividing by 3, you passed. If I average those out the correct way, where this guy's worth 100 points and the other two are only worth 10, you didn't pass. You're going to have a much lower grade, very close to 50. That's the same case for atoms in isotopes in a periodic table. You often have guys who exist in a larger abundance than other ones. And you have to take that into account. You have to include the different abundances of each isotope. Just like in a weighted average of your grade, you have to take into account the fact that tests are worth more points than worksheets and quizzes and labs. So they affect your grade more. Now you're going to see that with my first example. When I do carbon, 98.9%, I think, somewhere around that, of all the isotopes of carbon is carbon-12. Hence the fact that carbon average atomic mass is 12.011. It's very close to that number. Just like if I were to average up these numbers I just had up on the board here a second ago, your average would be very close to 50%. It would not be very close to 100% because only 10 points of that. It was only worth 10 points. Okay? All right. Take a look, by the way, before I go on and do that first example, let me just show you that almost all the periodic table elements have multiple isotopes. Take a look at some of the examples. And sometimes not just 1 or 2, but 4, 5. All right? Lithium exists as 2 isotopes. Carbon as 3. Fluorine only has 1. There are guys who only have 1. 3 for him, 4 for him. Let me just ask you a few questions about a guy like sulfur. How many protons are in sulfur? This sulfur right here. How many protons are in that one? Sulfur 34. 16. How do you know there are 16? Because you look at the periodic table and you see sulfur up there has an atomic number of 16. How many neutrons are in this guy? 18, right? How many protons are in sulfur 33? 16. How many are in here? 16. How many are in here? 16. But how many neutrons are in sulfur 32? 16. How many here? 17. How many here? 20, actually. I tricked you. All right. Let me ask you this question. Looking at this number here, all right, we have carbon-12, carbon-13, and carbon-14. Since the average mass is so close to that guy, who do you think most of carbon-12 exists as? Right. Who do you think most of lithium exists as? Right. See? Because that number, the average, is very close to that. All right, and we'll find that out with the first example we're going to do here. All right, copy that guy down. By the way, I'm only going to do 2 examples on the board, and I'll be done. I'll get a worksheet, which you'll have about the rest of this period to complete. And then I have other things we have to do. Remember the other ones we didn't finish because we only had a single period last week. We will do those other worksheets too. Okay, now I'm going to go off on another tangent here. And it has to do with percentages. Okay? If I look at these percentages, I think right now you have to realize something before I get off into this, before I go off my tangent. I can't just take this guy's mass and this mass, add them up, and divide by 2. You all agree that that's not going to work, right? if most of your grade is due, if 98.89% of your grade is due to this grade, and only 1% of your grade is due to that one, you know your grade is going to be very close to that one. Okay? So that's the reason why. Now let me talk about how we would get a percentage. Okay? What does a percentage mean? We already saw how to calculate a percentage. Remember back in the when we were first talking about this with the percent error. Part over the whole times 100, remember? All right, well, very similar here. Very similar. We have to talk about this. Again, it's a tangent. It's not really important to, I'm going to show you how to do this in a second anyway, but you should understand what a percentage is. Say I wanted to get 50%, don't write this down, 50% of 40. I think everybody knows what the answer to that is. What is it? 20, okay. What if I wanted 10% of 40? What would it be? Anybody know that one? Yeah, you should know it. It's 4. And the reason I wanted to point both of those out, well, first of all, the 10% one's an easy one for tip calculating. You guys don't have to leave tips very often, but you go to Snowball, you go to prom, and you go out for dinner, all right? So a lot of times, you know, one of the reasons why waitresses hate waiting on prom people, because you guys don't, first of all, you either don't tip at all, or you don't know how to tip. So if you work at a restaurant as a waiter or a waitress, you don't really like to see a bunch of kids coming in for prom. They usually treat you like crap, mainly because they know they're not going to get a right tip from you. If you wanted to get a tip, what should you leave? Anybody know? I heard everything from 10 to 20 out there, right? Generally, 15 is acceptable, all right? Shouldn't leave 10 anymore. It used to be 10, but it's really not 10 anymore. 15 is acceptable if it's really good, probably 20. How could you get, say your bill is $40. You got 10% of that. You want to leave 10%. That'd be $4. See what I did there? It's easy because all you have to do in all these cases, if you want to do it, is you simply move the decimal place over 2 spaces and multiply by that number. What's 0.1 times 40? 4. It's 4, right? It's 10% of 4. It's 4. So if I want to leave 15%, what would I do for a little trick here? What would I take? Half of that 4, which is what? 2. So what would you leave for your 15% tip? 6. What would you leave for your 20% tip? 8. You see? If your bill was $40, you'd leave 8 for 20% if it was really, really good service, if you liked her, and probably 6 if it was average, and 10 if you wanted to be insulting. But most people don't leave 10 anymore. All right, so my point is, percentages mean out of 100. Out of 100. So like 50 out of 100, all you got to do is, what is 50 out of 100? What is that in a decimal form? 0.5. So that's what we're going to do. We're simply going to change these into a decimal form and multiply them by their masses. We're going to take 98% of that mass, 1.1% of that mass, and then what will I do with those two numbers to get the full mass? What do you think I'm going to do? Add them up. Yeah, I'll just add them up. Because 98, this percentage plus that percentage will be 100%. All right, so I have to, that's called a weighted average. This is called a weighted average. That's what you would do to get a weighted average. A lot of your teachers might do this. Obviously not with ugly numbers like this. But there are teachers who say, I want homework to be 30% of your grade. I want tests to be 30% of your grade. I want this labs to be 10% of your, they'll do that. So when they get your average for all of your labs, they multiply by 0.3. And then 0.3 they'll multiply by for, to get 30% of your test grades or whatever, your lab reports, your whatever. And then they'll all add up to whatever your grade is. I don't do that. I use a total points basis, which works out pretty much the same way. All right, so here's what we're going to do. We're going to turn each of these guys into a decimal, which means basically dividing by 100. Move the decimal place over 2 spaces. So for carbon 12, it'll be 0.98892 times his mass of 12 AMUs. And if you do that, I have this first one worked out for you, so you don't have to get your calculators out. If you do that, you get 11.867 AMUs. And that's rounded off to the correct number of significant figures because 1, 2, 3, 4, 5 significant figures, 5 for him. I don't include 12 because he was our standard. So, okay? What will I do for the next one? Careful on this one. I've got to get the decimal version of this percentage to multiply him by his mass. What do I get? Do I get 0.1108? Because that's what many of you will do. What do you actually get? So for carbon 13, you get 0.01108. You have to move the decimal place over 2 spaces because you have divided by 100. That's what a percentage means. It means out of 100. 50 out of 100 is 50%. Times his mass, which is 13.009928 AMUs. And I have that one worked out also. It is 0.1442 AMUs. Now, I took 98% and 0.011%. If I add them up, I get 100%. If I add these up, I get 100% of my average weighted atomic mass. Without using a calculator and without doing any math in your head, what do you think this answer is going to be?
0.011.
Exactly. It's going to be the number up there in the periodic table for carbon. Now, of course, you should do it because this is a great way to check your answer. All right? If you add these up and it doesn't come out to be the number up there, you did it wrong. By the way, you may notice something. Significant figures say for adding and subtracting, what's the rule? Least number of what? Decimal places. So I drop him. And this comes out to be exactly 12.011, which is exactly the number up there. Don't expect that to happen all the time. In the worksheet you're going to do in a few minutes, don't be shocked if you got 12.010 or 12.009. I mean, if it's very, very close, it's okay. All right? The reason that happens is multiple reasons. Actually, it has to do with rounding off. Has to do with the fact that different periodic tables actually have different numbers for these, depending on how old they are. All right, and it also has to do with the fact that how many decimal places, how many significant figures I give you in the problem. If I don't give you enough, you may get a slightly different answer from the one on the, but it should be very close to the one on the periodic table. Okay? All right, so there you have it. Everybody knows what you're going to do. You're going to do that every time. I'm going to do one more example for you, but in every case, you're simply going to take a weighted average. And that's important to kind of know how to do a weighted average. You don't just add them up and divide by 2 or 3 or however many you have. You have to take that percentage of this mass, that percentage of that mass, add them up at the end, and that's your answer. And don't divide by 2. All right, try this one now. Copy that guy down. Oh, by the way, in case you're wondering, that carbon one, the carbon one I just did, I told you a minute ago, carbon has 3 isotopes, and it does. But the other isotope, carbon 14, is such a small number, it doesn't even show up in the significant figures. It's so small of a percentage, like 0.00001%, that even when you go and add them up, you won't get a difference from 12.011. That's why it's not included. It's such a small amount of it. All right, everybody got that copied? Same basic idea as before. I'm going to move decimal place over 2 spaces. So tell me, what 2 numbers am I going to multiply together here, Maddie? For copper 63. Correct, 0.6917 times. Right. And you get 43.53. All right. Now for copper, 65. Ronnie, what am I going to multiply together for this one?
0.3083.
Times
64.195
All right. And I have that one worked out as well. You can check it on your calculator if you want to. It's 20.01 AMUs. This is one that will not come out to be exactly the same as the one on the periodic table, but it will be awfully close, as you'll see. When you add these guys up, you get 63.54. And on some periodic tables, you will see that as the atomic mass, the average atomic mass of copper. But on ours up there, it is 63.546. That's fine. All right, it should be within a tenth, less than a tenth of a difference, probably usually less than a couple hundredths of a difference. That would be fine. That is your answer. That is the average mass. So here's what this is really saying. By the way, to sum it all up in a nutshell, here's what this means. If I'm holding in my hand a handful of copper, 1 mole of copper, let's just say I have a mole of copper, how much would 1 mole of copper weigh? Remember what we did the other day. How much would it weigh? 63.54 what? Grams. And that would be about a handful of copper. Okay, 63.54 grams I could hold in my hand. Of that, 63.54 grams, 20 grams of it is copper 65. And about 43 grams of it is copper 63. Okay? But I can't separate them out. They're there. All right? They're there. Matter of fact, you know what they're doing right now? Well, supposedly doing right now in Iran with uranium and centrifuges. You ever hear about, you know what they're doing? Trying to enrich uranium. Uranium exists as multiple isotopes, one of which is fissionable, and that's the one you want to get. That's the one you want to get up. But to do it, you have to separate. It's a very tedious process to separate it from its other isotope. So to get uranium-235, I think that's the one that you want, you have to send it through all these centrifuges to try to get it to separate out from the other ones. The kind of uranium we use in the power plant up here, it's only 3%. It's only about 3% of the fissionable uranium. All right? The other 97% is not. And that's still enough to cause a chain reaction, but it's not enough to be weaponized. To actually make a weapon out of it, to make a nuclear bomb, it has to be much higher than 3%. It has to be, I forget the exact number, maybe 20% or something like that. But I'd have to look it up. But that's what they're trying to do, separate those isotopes out. Because normally, if you're holding a handful of carbon or a handful of copper, you've got multiple isotopes that you're holding in your hand. All right, you can't really separate them out for the most part. But the average mass of any one of those guys is about that for copper. All right? Okay, now let me give you those worksheets.